The 6.4 lecture deals with vector arithmetic and what is called the dot product. So we'll just get into it. One of the things you have to understand, there's a vocabulary word called scalar and scalar multiplication. Basically what it's telling you is that the scalar is 3. And so if you had a vector, you put the 3 in front of the vector, and it's similar to the distributive property. If you take 3 times 2 and 3 times 5, you get 6 and 15. So nothing super new, but just be aware of that. All right, u is 1, 2, and we're adding to it the 3 and the 1. And so I would do 1 plus 3. Those are the first things. And the 2 plus the 1, those are the second things. And my answer is 4, 3. Simply add the first position numbers and add the second position numbers. When you subtract, if you write it out, just be really careful about what's first and what's second. So u is 1, 2 minus 3, 1. If the order would change, our answer would change. Subtraction is not commutative. So then I would write this out as 1 minus 3 and 2 minus 1 for a final answer of negative 2, 1. 2u simply means put the scalar in front of u, and you end up with 2, 4. If you want some time for part D, maybe to do a DIY, pause the video now. Otherwise, I will just keep doing this problem. So off to the side, I would figure out what 2u is, and 2u we just did in the previous problem. So again, that's 2, 4. And 3v, multiply vector v by 3 would be 9, 3. So if I was going to subtract, I would do 2, 4 minus the 9, 3. And so doing that, I would get 2 minus 9, 4 minus 3, and I end up with negative 7, 1 would be my final answer. Okay, for the next few examples, we have vector v. And they've already drawn vector v in there for us, so it's on the graph. And what they're asking us to do is add u plus v. So if I were to look at this vector, I would normally go 1, 2, 3 to the right, 1, 2, 3, 4, 5, 6 down. So the vector would look, that's bad. The vector would look like that. That would be vector u. So all we're trying to do in this problem is give you an understanding of how this works and give you a visual. Okay, so right where the arrow ended, I'm going to go 3 to the right, 1, 2, 3, and down 6. 1, 2, 3, 4, 5, 6. So if I draw my best straight line, now that's vector u, this was vector v, and this is u plus, I should write it the same way they did. They called it v plus u. And so vector v plus u is ending at 5, negative 1. So I moved it manually. Well, algebraically, if we did the work, 2, 5 plus 3, negative 6, 2 plus 3, 5 plus technically negative 6, double sign, I know, and that's 5 minus 1. So mathematically, I got the same answer as the visual representation. So the next one is supposed to be 2v. So looking at 2v, that's this one is v, and then I do another one. So I go up another 1, 2, 3, 4, 5 over 2. And so there's another v. And so I end up at 4 to the right and up 10. So the visual is 2v, same direction, same length. Well, the vector or scalar multiplication here, sorry, v is 2 comma 5. And so you end up with 4, 10. And again, the visual and the mathematics work. So number 4, compute negative v and then graph the result. So if v goes up and to the right, negative v would go down and to the left. So it looks like I'm finishing at negative 2, negative 5. And so if I put a negative 1 in front of 2, 5, and I multiply, I get negative 2, negative 5. So when you look at a negative vector, go in the opposite direction. Instead of going right and up, you're going to go left and down. So the same thing here. If I did u was 3, negative 6, so instead of going to the right 3 and down 6, I'm going to go to the left 3 and up 1, 2, 3, 4, 5, 6. And it looks like I ended up at negative 1, 11. Well, if I write this out, v is 2 comma 5 minus u, which is 3, negative 6. Let's see what happens. So I end up with 2 minus 3, 5 minus negative 6, negative 1, 11. So it worked out again. So those problems, we're doing the mathematics, but the visual is to kind of make sure you have the right answer. Then we get into what is called a dot product. And when you look at a dot product, u dotted with v right here, notice you do the first ones and multiply the second ones, but the key is to make sure you multiply those two answers together. So let's go ahead and try this one. You're going to do 6 times 1 plus 2 times 3, and so I get 6 plus 6, which is 12. And this is called a scalar, just a number right here. They're talking about it. It's not a vector. It's just a plain old number. Too often students do dot products and they write it as a vector, but you add the two answers together. All right, so this is a DIY. I want you to do that on your own, so pause the video now. All right, so what I would do is take my 0 times 3 plus 4 times negative 2. So this is 0 plus negative 8, which would just be negative 8. All right, this last page of notes, we start off with an angle between two vectors. It's a little formula. So it's the dot product on top the two magnitudes, and then you throw them into the formula. So first, I would find the dot product of u and v. So I take the 4 from the first one and multiply by the 3 in the second vector. So first things multiply. Add to it 3 times 5. So that's 12 plus 15, which is 27. Then we're going to do the magnitude of v, which is to take the square root of 3 squared plus 5 squared. That's 9 and 25, so that's the square root of 34. And then we do the magnitude of u, so that's 4 squared plus 3 squared. Again, these are component forms, so you don't have to do the distance formula, just square the first and the last number there. So this ends up being the square root of 25. Well, that's nice, so I'm going to call it 5. So then the formula is the dot product on top, and the two magnitudes get multiplied on the bottom. Now this one, the magnitudes are a little more difficult to type in, so on the calculator, I would probably do 5 times the square root of 34. So that's my bottom number. So I'm going to take 27 and divide by the denominator. So I'm just going to second negative. And then you should get a decimal. And then when you go second cosine, second negative, I'm getting 22.16. Now, one of the things I like my students to do is to go ahead and draw a picture of this. So vector u is 1, 2, 3, 4, 1, 2, 3. And vector v is 3, 5. So we're going to find theta. Now, oops, sorry. So I went 4 to the right, up 3. I went 3 to the right, up 5 with my two vectors. So we're going to find theta. Now, we always find the one that's between 0 and 180 because inverse cosine can only produce answers between 0 and 180. If somebody wanted this angle, you'd have to do the angle minus 360, or 360 minus the angle. But anyway, this just helps me estimate because we're pushing a bunch of buttons on the calculator. That looks like it could be about 22. It's about a third of a quadrant, so that looks good. All right, the next one is a DIY. So go ahead and pause the video and then come back and check your answer. Okay, so we're going to go check the answer. If you do a dot product of the two vectors, you get 3. U has a magnitude of 3, and V has a magnitude of root 37. So when you put that all in the formula, you get a decimal kind of like this. Inverse cosine it, you get 80.5. Now, if you draw a picture of it, the first vector U goes 3 to the right. So it's right along the x-axis, and 1, 6 would be something like this. So you can see we're almost a quadrant, which is 90 degrees, but not quite. So 80 does make sense. So the last thing with orthogonal vectors, if you do a dot product and it's equal to 0, we say it's orthogonal, which is a fancy word for perpendicular. But a lot of times our vectors would meet kind of like this, rather than what we learned back in geometry, like if you had a line here and another line where they actually kind of intersect. They don't, their initial points aren't touching, it's actually crossing over each other. So we need another term for this, and it's called orthogonal. But essentially it's perpendicular. So on this first example, I would take the 2 times the 6, and I will add to it, don't forget to add when you do the dot product, negative 3 times the 4, so this is 12 plus a negative 12, so I get 0. So yes, orthogonal. Now if you graph these things, 2, negative 3 would be about right there, and 6 would be about right there. And yeah, you know, they kind of look like it might be close to a 90-degree angle, but this proves it without a doubt. So let's treat the next one as a DIY. So pause your video now. So take the negative 5 times 5, negative 6 times 6, and you get negative 25 and negative 36, which is negative 61. So no, they're not orthogonal. So I'll show you one more thing. This one, that's one of the vectors, and the other one is u is 1, 2, 3, 4, 5 to the left, 1, 2, 3, 4, 5, 6 down, be about right there. So clearly these two vectors can't be orthogonal because they're almost a straight line. So one of the things you can do is calculate the slope. Now remember, slope is y over the x. Now technically, because it's component form, 0 and 0 are the initial point. Well, I don't need to write minus 0, so I end up with just 6 over 5. And then over here, I can do the slope of v, which is the y over the x. And here, they're not necessarily parallel as in next to each other, parallel never touching, but because their slopes are identical, they are parallel. Now up above, I can do the same thing. I can do the same thing with these slopes. So the slope of u is negative 3 over 2, and the slope of v is 4 over 6, y over x, which is also 2/3. Now, these two things are what are called negative reciprocals, and that means they're perpendicular. Well, we already identified them as orthogonal, but I just wanted to show you finding slopes of vectors is it when they're, especially when they're in component form, is just putting the y over x. So that's it.